I'm just going to make one small comment today about logistic function. I already have a whole other video about that I posted like 6 months ago, but I was rewatching it again today and I noticed that I didn't say one thing that I should have said. I'm not going to explain logistic function to you today. If you still haven't watched that, you can go do that, because in that video I explain how the logistic function comes from a differential equation that wants the derivative to be zero when y is 0 and y is some other number. So that makes a function with two horizontal asymptotes, which looks like an exponential function in the first half, and then it looks like another different exponential function on the other half. And that is really useful to model a lot of situations in life, like I mentioned in the other video. So here's the solution to the differential equation. I'm not going to go over that because I've already done it, but here is the answer. This is the logistic function, the solution to this differential equation, which is the same as the first one, but with the names of constants slightly changed. Then I also go over this step by step in the other video, how you can turn this way of writing it into this one, which is also just a matter of rewriting. Like, for example, you can multiply the fraction by e to the minus kt here and here, so that in the end you only have one exponential factor instead of having two. Stuff like that. It's a step-by-step process. If you want to follow it, go to the other video, but if you're willing to just trust me on it, then we can start from this one, because this one is the logistic function as it appears in the formula booklet for the AI high-level course, which is the only one of the 4 courses that has this content. However, the other ones are also obviously allowed to use them in their IAs. And also, and this is what I wanted to talk about today, the way that the logistic function is written in that formula booklet is not necessarily the same way that you have to use it. So sometimes for using this in an IA, a student will look up the formula on some other source that is not the formula booklet, and sometimes it comes written like this. I would like to explore this version of it a little bit today, because I think that it can be a little prettier than the previous version, because the constants will have useful meanings that we're going to be able to explore. Of course, if you want to come from this one to this one, it is also just a matter of doing a small manipulation. So you're going to take that constant c that you have in the denominator, and you're going to call it e to the power of k times t0. So that when you multiply that by the e to the power of negative kt that is already there, you're going to add these exponents and then factor out a negative k, which leads us to this other formula. And you have the same number of parameters too. This is important. You have L, C, and K here, and in the other one you have L, K, and T0. Okay, so what are we able to say about the constants in this formula? One thing that you might want to try is to calculate h of 0, which is the y-intercept, always an interesting thing. But this doesn't result in anything particularly interesting, because you still have all of your 3 constants there. But then again, it also didn't result in anything interesting in the other formula, because it just became L over 1 plus C. It was 2 of the parameters instead of 3, but in any case, not something that is giving you a straightforward information. So none of these parameters mean the y-intercept. Something that might be a little bit more interesting to explore is what happens to h of t when t becomes very large, because that should be the value of the second asymptote of the function. Okay, so what happens in that case? You have the L in the numerator, and then here you have 1 plus, and then this t is getting very large, which means that the t0 being subtracted is not really doing anything much right now. So t minus t0 is just a really large number multiplied by a negative sign, which means that this whole thing here is going to 0. Yes, I am assuming that k is a positive constant, but if it was negative, you would just do everything backwards, and in the end, the whole thing would turn out to be the same. This one wouldn't have that term as 0, but in the end, after you've done all of the parameters, it would turn out to be the same, just backwards. And this one is just L, which means that the parameter in the numerator of the logistic function has a very explicit meaning. It is the y value of the second asymptote. Okay, so maybe we can learn something else if we look to the left side instead of the right side and the other horizontal asymptote. That is the limit when t is going to minus infinity. And again, the t0 is not going to do anything, so this exponent here is minus infinity, which with a negative sign becomes infinity. And e to the power of a very large number plus 1 is still large, but that whole thing is in a denominator. So I'm dividing L by an extremely large number, which makes it 0. So the first asymptote in this formula is 0. If you want to make a logistic function that has two different asymptotes like this, neither one of them is 0, you're just going to have to do a vertical translation in the end. Of course, that would be a fourth parameter, and I don't want to deal with that right now. But I do want to do something else because there is a third thing that could be interesting here. H of 0, when we calculated the y-intercept, didn't turn out to be interesting. But if we calculate h of t0, then this part of the exponent will be equal to 0. It's going to be just t0 minus t0. So that can be interesting. E to the power of 0 is just 1, right? So we're talking about L over 2. The function has two asymptotes, one at 0 and one at L. So L over 2 is in the middle. It is this point here where the symmetry is, and the x value of that point is t0. I wrote down x value of the inflection point because that's where it is. It is a point when the thing changes concavity. And it's always nice to have a proper word to write down to refer to things, right? It's much better than writing down what I just said, which is the point where the symmetry is. It sounds very vague. Okay, so that's two of the parameters having a very specific meaning. The third parameter, which is the k, is not going to have so much of that specific meaning, but if you're trying to make a specific logistic function, then you can always use that third extra parameter to force your function to go through a specific point with coordinates x and y that you know, after you've already figured out the values of the other two parameters. So I'm going to give you an example of that right now by going back to the example that I had in my other video. The first example there was life expectancy versus GDP. And at the time I used regression because that is the first thing that I try every time that I have a bunch of points like this. But I did mention in the video that I was disappointed in the result of this regression because of where the asymptote is. There are a lot of points above the asymptote of this logistic function, and the asymptote on the right side is supposed to be the carrying capacity. It's supposed to be a value such that in the context that you're studying, there are real world limitations why the points are not going to go over there. And here are my points doing exactly that. So that was disappointing. And in this case, the real world limitation was because the y-axis meant life expectancy. So you see 75 years old here. This is supposed to be 80 and 90 years old. The asymptote is basically putting a limitation on 80 years old being the life expectancy in a single country, which doesn't sound that bad, but we do have points with life expectancy bigger than that. However, we also do have a natural limitation, right? Because people can't live forever. So I'm not claiming that this shouldn't have a limitation. I'm just saying that 80 is not the proper limitation. It should be a horizontal asymptote a little bit higher than that. So I have both versions of the formula here so that I can choose which one is going to be more appropriate for what I want to do right now. First of all, I want to put my asymptote at 87, which looks consistent with what I was drawing by hand, but that can be done in either one of these formulas. I can just put L equals 87 and it will mean the same in both. But as for T0, it was the x value of the inflection point, and the inflection point doesn't really have any meaning in my context. It's somewhere around here. So maybe for this case, I want to use the other formula on the right, because on the other hand, h of 0 is something that I can kind of see. I'm going to put 60 years old, which is also what this green one is doing, and it looks pretty much okay. What doesn't really look okay is that I wanted to start from here and go up a little bit faster than the green one is doing, but maybe I can achieve this effect by dealing with the other parameters. Okay, so in this formula, h of 0, which I want to be 60, is going to be 87 over 1 plus c times e to the power of 0, which is just 1. So it's not like the parameter c itself has a specific meaning, like c is the y-intercept. It's not like that. But once you have the L, you can use the c to find the y-intercept or vice versa, which is what I'm doing right now. C is 0.45 and I already have L equals 87. I still have freedom in the value of K. So now I'm going to go back to GeoGebra and give myself that freedom to find by trial and error which value of K looks best. Okay, so I've typed it here like this function g of x. I typed 8.7 instead of 87 just because of the scale of my vertical axis. And then we can start to change the value of k to see what happens. Look, negative values of k make the function turn backwards, like I mentioned before in this video. But I want a positive value of k. You can see that all of them have the horizontal asymptote at the value that I wanted, which is above the life expectancy of all the points in my data set. And it changes the way that it passes through the points, even though all of them have the same y-intercept, which was also done intentionally. So I think that I'm going to choose this value here because it just seems to go nicely through the points. And then what I have here is a picture with both functions together for comparing, right? The first one that I got with regression in the other video, and this one that I just got right now by manipulating the parameters to visually fit what I thought would be good. Comparing things is generally good. If you're writing an IA, there is this specific mention in the rubric D, level 2, meaningful reflection. And then he gives a few examples of how to show meaningful reflection. One of them is this, comparing different mathematical approaches. So how could you compare these two things that we were just looking at? First of all, you should compare them visually, which is what we were just doing right now, talking about how the asymptote of one doesn't really make much sense. You could also say that the new one passes better through the first points, the ones more on the left, but the second one passes better through a second set of points kind of here, right? This is what I'm talking about. The regression function is better in this area, but our trial and error function is better in this area. So that's a kind of visual comparison that you can make. And you should also try some sort of numeric comparison because you have knowledge about the coefficient of determination. So you should definitely calculate the coefficient of determination for both of these functions and see which one is bigger. Of course, depending on the technology that you used for the regression, of course, the regression function is going to have the bigger coefficient of determination because these technologies are doing this intentionally. But if my function that I chose specifically has a coefficient of determination that is smaller, but not a lot smaller, it can be a good trade-off to get one that is slightly smaller but visually fits the data in a way that makes more sense. That is the kind of comparison that you're looking for in reflection, okay? It's not just applying things to a formula, but it's thinking about them in multiple ways and talking about them exactly like we're doing right now. So here I have the second example that I used in the previous video, which was the speed of computers getting faster over time. So the horizontal axis is time here. And for this one, I'm going to use the other formula because the image is not really giving me a lot of information. So in order to have some sort of result, I am going to assume that this last point in the picture is the inflection point. I'm going to assume that from here, it starts to decelerate. So what that would give me is two things. It would give me the L, which is the asymptote, would be twice the value that we see in y for this point here, which is 1.5 times 10 to the 11. So that would be 3 times 10 to the 11, which is twice of that. And for the x value of the inflection point, well, these are years, right? So maybe 2018 in the scale that I'm seeing here. And then you have k as a free parameter to put in GeoGebra and search by trial and error. You can also just pick a point that you say you want to be perfect. Say I want my function to go exactly through this point, and then I will use this point to find k. by substituting its coordinates in the function that already has the 3 times 10 to the 11 and the 2018. This can be done, but I just don't think it's worth it, because before you do the calculation, you don't know what the resulting function is going to look like. You don't know if passing through that specific point is going to be a good choice. And if you do it the other way, if you leave it free and then choose it by trial and error, you can also try to visually make your function pass through the point that you wanted, right? You can do that and more. So I don't think it's worth it to do this part as a calculation. So just like in the other video, I'm not going to do this one. I'm going to leave it as an exercise for you. Here is the image if you want to screenshot and give it a try in GeoGebra. But I was also mentioning how important it would be to compare the two results. And I said that one of the ways that you should compare them is by calculating the coefficient of determination. A lot of technology that you use for regression already gives you the coefficient of determination. Not all of them, but some of them do. But if you want to calculate the coefficient of determination of a function that you created by other means, like we just did with this new one, then you have to calculate the coefficient of determination yourself. And that is very good motivation for learning how to do that by hand, rather than just saying, oh, it's a number that comes from the calculator. I don't recommend looking into that without a reason, but this is a reason, so it's good. And I do that also in my other video. But that's just a small part, so I'm just going to replay it here so that you can see how to calculate the coefficient of determination by hand. So the thing is that when we're doing regression, any type of regression, and here I have an example that looks quadratic maybe. You have a set of points. I have 4 blue points here, and I am trying to put a quadratic function that kind of goes through them the best possible. But how am I going to determine which function is better than another function for those points? Is that I'm trying to minimize something. This thing, which is the vertical difference between the point and the function for that value of x. Okay, so it's vertical differences. And also we are going to be trying to minimize the sum of the squares of those differences. Now, sometimes people justify the use of the square here because it loses the sign, positive or negative, because we don't want these things to cancel out. Like if this point is above the curve by this much and the other one is below the curve by kind of the same amount, this is not the same as if they were both exactly on the curve. A positive difference should not cancel out a negative one. So if you square them, they all become positive. So when you add them up, they don't cancel out. But anyway, how does it come up in the formula? What are we doing here? So the y's are the actual points, the data points that you have. And the f's are the predicted values for the x's of the points. What would be the predicted y? So this is the point in the curve, and this is the point of the point, the data point. That's the difference between the two, so it's a vertical difference that's squared, and then you're adding them all up for all of the points. That is the sum of the residuals. And then the other thing that you're also going to calculate is very similar. You're also comparing the y of the actual points, but this time you're not comparing it to the y of the function at that x. You're comparing it to the average of all the y's of all the points. That is what we calculated here in the beginning. Just take all the y's, add them up, and divide by the number of points. That's the usual average. And then you do this sum of those differences squared. And then you put one of those on top of the other, and you do 1 minus that number. Remember, the residual is just the difference between the point and the function for the value of x of the point. So 13 over 14 as compared to 1, the difference is 1 over 14. And then 31 over 14 compared to 2, well, 2 is 28 over 14, so the difference is 3 over 14. And the difference between 3 and 20 over 7 is 1 over 7, which is 2 over 14. Now, this is the average of the y's, which I remember I am also going to need for the calculation. And now I'm going to go through that Wikipedia page again, but with my numbers. So I should take my residuals, which are these three, and square them add them up, and then by some magic here, a 14 canceled out, so the answer is 1 over 14. That's the sum of the squares of the residuals. And the second calculation became a lot more easy just because the average was 2, a very pretty number. So the sum of the total differences was 2. When I put the 1 over 14 and the 2 into this last formula here, I get 0.964, which is then the coefficient of determination, that is r squared. But the thing is that GeoGebra does the regression, he doesn't tell me the coefficient of determination for what he found. And that is the whole reason why I was talking to you about it in the beginning of this video, because if he is not going to calculate it, then I want to calculate it. I want to know what the coefficient of determination is for this green curve so that I can compare it to the red and to the blue that came from other softwares. You see, I have a reason to be doing this. So yeah, here are the calculations. The 0.00884 and stuff is the function that GeoGebra gave me. It is the green function. So I'm just following the steps that I was talking to you about when we were reading the Wikipedia page. It is the same steps that we followed by hand on my linear example. Okay, so we are going to calculate the sum of the squares of the thing that compares it with f, the thing that compares it with the average, and then we're going to do this. Except this time, of course, I let Google Sheets do the calculations for me, and it comes up with a very, very big coefficient of determination, 0.991.